smart contracts. This was taken from a PODC 2017 paper. If you want to see more detail, it comes from people half from Yale and half from Brown. So as you've seen before, and you'll probably see again, we're talking about distributed ledger, append-only, not just financial. Everyone agrees, and tamper-proof. And these things are kind of constant for everything that we're doing. This isn't working. Okay. Thanks. So this is what a blockchain looks like. To a first approximation, I realize this is much less detailed than some of the other pictures, but we're pulling back to a kind of higher level of abstraction here. Hashes and signatures make things tamper-proof. There's a distinction that people make between a permissionless blockchain, which is like an oriental market, where you don't know who you're buying and selling from, and if somebody sells you bad tomatoes, you have no recourse. Pretty much, most of the cryptocurrencies are public. Anyone can participate. No central authority, which is actually kind of a lie. And this is these are the things that mostly people talk about, but arguably private ones are going to be more efficient, more influential in the long term. A permission blockchain is more like a one of these over air-conditioned California supermarkets, where if you buy a tomato and you don't like it, you can bring it back, and they'll apologize and give you your money back.
What is this?
What's it?
Which supermarket is this?
Whole Foods. Yeah. I don't think they have Whole Foods in Israel. So, basically, the reason I'm saying this is that I'm going to be talking about public blockchains. But what I'm saying is applicable to private blockchains, but things change in interesting ways. And I'll try to comment on this as we go through, but I won't really have time to do it justice. So I'm going to talk about permissionless because it's a more challenging environment. But there are interesting variations here. So again, at this very high level of abstraction, a blockchain has a collection of clients. That's one role that you can play. There's a collection of miners. And there's a collection of validators. Now, these roles are kind of fluid. So a miner can act as a validator, a client can act as a validator. But I want to keep the roles separate, even if the parties who do this might be the same. So basically, clients send their transactions. They're going to use stars to represent transactions to miners. The miners then package up the transactions into blocks. And then they have some kind of consensus protocol. We just heard about a lot of detail about how some of these things can work. And they do some form of distributed consensus to pick which of these competing blocks actually gets through. And for our purposes, we don't really care how these are chosen. Only that one winner eventually emerges. So of course I'm covering up a lot of detail here, but that's because I want to focus on different things. So what do we choose that for? Well, what we want to do is we want to append it to the end of the blockchain. So this is our blockchain as it grows over time. Validators are the parties who go through and make sure that everything works. And for my purposes in this talk, that's everything you need to know about blockchains. Now, it's true that I'm covering up a little bit of complexity. This is my view of a lot of the work that goes into blockchains. But fortunately, we're going to try to pretend that none of this matters for what we're doing. So we're back in the smart contract world. Scripts on the blockchain, not contracts, not smart. Same thing I've said before. Smart contract looks something like this. Again, it's like an object in a programming language, in an object-oriented language. we have long life state. This is something that persists basically forever. They're a collection of built-in data types, and this is important. In a language like Solidity, you can't define your own data types. You can define your own contracts, which can sometimes pretend to be data types. But basically, there's a fixed collection of data types, which will turn out to be a good thing. In this particular example, we track who can vote, who voted, what the choices were. So the persistent state is a map from address to vote. We export functions that manipulate the state. Here, a voter can say, I want to vote for proposal number 3, for example. We do something like say, well, okay, so I'm going to see who the voter is. If the sender already voted, then I'm going to roll back. Then otherwise I'm going to record the vote. I'm going to say, yeah, this person voted, that's their proposal. I'm going to stuff them in. Maybe it's a weighted voting. Some voters are more important than others. The point of this is that you have a bunch of variables that represent long life state, and we read and write it. So now we'll go back and revisit something like Ethereum, where we have smart contracts in addition to simple transactions. So the miners assemble the contracts, and they apply them one at a time to compute the new states. And so between each, we basically run these in order. And when we package up the block, we also include the last state. Of course, it's an optimization. You could go back to the beginning of time and replay all the transactions if you had to, but why would you do that? So now we've moved into a world where the blocks include both contracts and a state. So what the validators do is validators have to go back and replay all the block contracts in order. So since nobody trusts anybody else, if you really want to make sure that everything is okay, then you go through and replay each of the function calls or transaction or contract creation, and you end up with a final state. You check and make sure that the state you end up with is the one that's on the block, and that's how you know that the block is actually valid. And if you're serious about this, you have to replay all of these things in order. Of course, there are optimizations, lightweight payment nodes, that sort of thing. But in principle, if you want to check these things, you have to go over. So for how long, if I write a contract today in the closing month of 2018, for how long in the future will this contract be re-executed, say in the Ethereum model? Basically forever. So that everybody who ever needs to validate my transaction has got to re-execute it. So it's going to be re-executed 100 years from now, assuming that Ethereum is still around 100 years from now. And so this is something that's important. And there's something even worse than re-executing everything forever, which is it has to be done sequentially. So the model says we line up the transactions in the order that the miner puts them in the block. We have to execute them in one at a time order. The thing about this is that this goes against everything we know about technology trends in hardware. So our processors aren't really getting any faster, unless you want to go out and buy specialized ASICs, which don't really work so well for smart contracts, but we're getting a lot more parallelism. So every year you get more and more cores, but you don't get more and more cycles per second. But the need to sequentially execute every contract that ever happened really means that improvements in technology are not going to improve your life, which seems to be kind of the wrong way to do things. So we can go back to the miners. So each miner executes the block's contracts sequentially when it computes the final state. They're paid by the client per step. So you might say, well, it's not so bad because you make money. But high latency means you have kind of a competitive disadvantage because everybody, at least in a proof of work-based system, is racing to prepare their blocks so that they can go out and join in the consensus. So anything that kind of slows down your block creation puts you at a competitive disadvantage against anyone who can create blocks faster. Validators, they have to execute every block's contract sequentially to validate that block. They don't get paid. This is more self-protection than anything else. So, we've seen that people sometimes cheat and don't actually validate things. But in principle, if you're a good citizen, you cheat, you validate. And every validator executes every contract forever, at least once. So, why is sequential execution so wrong, you might say? This is, we always talk about everyone assumes that concurrency is good, but we don't always stop and justify why this is. So, obviously, if you do things sequentially, you get worse throughput. You get competitive disadvantages. If one miner can figure out how to validate blocks in parallel, then it has a comparative advantage against one that can't. And so in the kind of Darwinian world of competitive mining, that means that everybody had better figure out how to do things in parallel because you're going to be at a disadvantage in getting your blocks onto the blockchain if others can package up these blocks faster. And as I said, you can't exploit multi-core technology. So every time the chip makers improve the number of cores, you're left out. So there's a couple ways we could approach this. One is to say, okay, so let's just, take. How about having the miner just pick all the transactions out of the pool, assign one to each core. Let's say we have some server with 64 cores, 128 cores, and just run them all concurrently. Anybody want to volunteer why this is not a great idea? Beg pardon? It's not deterministic. But why is it not deterministic? Yeah. Because there are data conflicts, basically. And so what happens, you would get an inconsistent shared state at the end. So I increment a counter, you increment a counter, and at the end it's been incremented by 1. So in our particular example that I flashed by at the beginning, voters could vote twice. So we don't like that. Another thing we could do is we could add explicit concurrency to the language. We could kind of embrace concurrency and say, okay, so why don't we put like fork, join, we could put locks, threads, priorities, all of these nice scheduling things in our smart contract language. And then I could sell more textbooks on concurrency. Anybody want to comment on whether that's a good idea or a bad idea? To start putting locks and all this locks and threads and so on in smart contract languages. Big pardon?
I think it's a bad idea. Like software developers are really bad using these primitives.
No. I think the proper answer to this is you just sort of scream. The literature is full of examples of sequential programs that are 10 lines long that have caused losses of hundreds of millions of dollars. Now imagine putting in race conditions and threads and locks, deadlocks, priority inversion, all that stuff. This seems like going exactly in the wrong kind of a direction for making smart contracts safe for the world. Another things we could do is we could do static analysis. We could look at the contracts and say, well, I can tell right away that these contracts don't have any conflicts, any data conflicts. So go ahead and run them in parallel. These two look like they have a conflict, so we'll run them sequentially. So this way we can kind of pre-process everything, get huge amounts of concurrency, And no, imagine, make things specific. Suppose you were going to do this in Solidity. What's the catch? Or is there a catch? Big pardon?
Latency?
Not just latency, but something even worse.
It's hard to analyze jumping between addresses in mapping, for example, so an adversary can exploit it. So it would be very hard to do it precisely. And if an adversary puts some conflicting code that is deployed on the address which is calculated at runtime, it would be hard to predict this.
Yeah. Basically, Solidity has the equivalent of function pointers, except with contracts. So you can have addresses that have variables, and you can basically call. You can jump there. So basically, the problem is, because you have this full Turing computability that we were talking about, it's undecidable in theory. And being undecidable in theory has never stopped anyone who does formal verification, but actually it's not practical. And so if you were anytime you would come up with something where you were jumping to a contract whose address was a variable, then you'd have to stop and say, I can't tell. So it wouldn't be very effective. Yeah?
I would just argue that 90% of all contracts don't do this.
Yeah. No, in fact, I would argue that you should probably be using a contract language that doesn't let you do that.
Yeah,
but
better.
yeah. But basically, I think it would be naive to rest our hope in future developments of this nature. So it's hard to do static analysis in a way that will turn out to be effective. But if anyone thinks that they can do static analysis in this context, more power to you. That would be a great result. But I'm going to assume that static analysis isn't going to save us. Contracts can call other contracts, and it's a dynamic call graph. You can't figure that out statically. So anytime you have one of these things, any contract could end up calling any other contract. And so if you start looking at possible contracts, then you end up looking at the entire assuming that Ethereum is still around 500 years from now. That's 500 years of contracts you would have to inspect. So as a kind of a alternative, I'm going to talk about the use of atomic transactions. This is going to sound like a bit of a digression, but I'll bring everything back. So, there people who do systems research have a kind of a secret that they don't want you to know, which is that all of the really effective systems ideas were really stolen from the database world. But the database people write in their own language. If you try to read a VLDB paper or something like that, it's very hard to understand what they're saying because they use different words for everything. It's not an Indo-European language as far as I can tell. They talk about latches instead of locks. When they say locks, they don't mean locks, they mean strict two-phase locks and so on. So it's possible to steal ideas from the database world, and you never get caught, because nobody speaks both languages. So we're going to steal the notion of atomic transactions, from the database people. The particular idea that we're going to steal is something from software transactional memory, where the idea there is that we're going to build highly concurrent software by using transactions to replace locks. And eventually, this idea, we're going to morph this into something that works for smart contracts. So the idea in this particular paper was we take the concurrent data structures and we instrument them to detect conflicts at runtime. And we can instrument them at basically any level we want. We can do read-write sets. It's actually much more effective to look at abstract properties like commutativity. So if I put two keys in a hash table and they're different keys, then those operations commute. So we can let them proceed in parallel, even if underneath they need to acquire short-term locks and things like that. So what we're going to do is we're going to take this idea and move it into minors. So what the miners are going to do is they're going to pull a bunch of contracts out of the memory pool, enough to stuff into a block, and they're going to execute those contracts concurrently in an optimistic, speculative way. But we will have instrumented all of the runtime data structures to detect conflicts at runtime. So if we detect a conflict, then we can either block that thread until the conflict clears up, or we can just roll back and rerun later. And so what we'll end up with is a concurrent execution, but serializable. So it says that all of these contracts were run in some parallel way, but from the outside it looks as if they ran sequentially. So in this way, we satisfy the requirements of the Ethereum-like world that all of the transactions in a block executed in one-at-a-time order, except that we physically do them in parallel. But the ones that happen in parallel are ones that it turns out at runtime didn't conflict. Yeah.
What do you mean by block here?
Oh, by block I mean the block of however many transactions that you're going to send into the consensus protocol.
No, here, conflict, block, rollback.
Sorry, this block here is not the same block
Yeah, I see. That's what
as block. It blocked me in the sense of stop.
And what happens next?
Oh, then what can happen is that one transaction comes along and it locks something while it's running. I come along and I want to do the same thing. It says, sorry, I'm busy. So I said, okay, I'll wait until you finish. You have to watch out for deadlock.
Okay, so conflicting transactions don't block each other, just one stops and waits for the other.
Waits for the other one to finish. And, this does have the other alternative is you say, oh my God, there's a conflict. I'm going to go back and just start over again.
How do you decide between the two?
Well, that's an engineering decision. If you have, if it's easy to recognize deadlock, then blocking works fairly well. What we're actually going to do is kind of a mixture of both of those things. So you have a choice.
So two validators running in different times, they could do different orders.
Well, we'll get to that. I'm only talking about miners right now. Only one miner wins. But you're right that there's.
The validator runs the whole thing again.
That's an excellent question, plus like 3 or 4 slides. Yeah, so serializable means that it's equivalent to some serial execution. That's another idea we stole from the database people. Don't tell them. So, for example, here we have a line in a smart contract where it says we'll go to this mapping, we'll take Alice and we'll add some to her balance. This is a map from strings to unsigned integers, for example. Here's the miner thread, and so this represents a core or a thread. So what it does is it says, okay, that's my intention. That's what I want to do. So I'm going to acquire an abstract lock for Alice. So everything relating to Alice in this map has to acquire this lock. So another thread comes along and wants to reset Alice's balance. That's going to cause a conflict because both of them need to acquire the same abstract lock. So what I'm going to do, I'm going to use this lock to block operations that don't commute. So I'm going to assume, somewhat pessimistically, that any 2 operations that involve Alice don't commute. That's not actually true because if you have 2, say, increments here, they actually do commute. But it's okay to be less precise than necessary. It's not okay to go the other way. So this way we detect conflicts. We know about mappings, so we can go in and go to the Ethereum virtual machine, and we can instrument all of the calls to mappings and give each one a lock. Here we have another thread. Let's roll back the film. Now another thread comes along and concurrently wants to reset Bob's balance. Well, that's okay because the blue thread now needs to acquire the abstract lock for Bob, and they're different. So they can proceed completely in parallel. So in this way, we can detect when we have two operations that commute and allow them to go on in parallel. So we allow concurrent operations that do commute in this way. The other thing that we need to do is we're going to keep an undo log, because if we go along and then realize, well, actually we can't do this in parallel because there's too many conflicts, I'm going to, here I have an operation where I'm going to add something to Alice's balance. I'm going to create an undo log which says, okay, I didn't mean it, let's decrement Alice's balance by this much. So this means that our operations have to have inverses. In general, this might be hard, but we're dealing in a very restricted domain. There's only 3 or 4 built-in types in something like Ethereum. It's all maps and integers and things like that. So it's not too hard for a compiler to figure out what the inverse to an operation is. If you don't know what it is, then we can just reset the original state. But in this case, we know that we can undo anything simply by subtracting whatever it is that we added before. So what I'm going to do is I'm going to register the inverse in an undo log. And notice that this will undo the updates to Alice only. So if I decide to roll back this thread's operations, I'm not going to affect anyone else. So there's a theorem here that says that if I have permission to actually do something, if I acquire a lock that lets me do something, then I have enough permissions to actually undo it by executing all the inverses. Okay, so at this point, I've acquired the abstract lock for Alice. I've recorded something in the undo log in case I need to roll back. Now I can actually go out and execute the operation. So I haven't touched any of the memory yet. So at this point, I know I have the lock. I know I can go and execute the shared memory. Now, notice that miners are not competing with each other. This is a single miner who's executing a logically single-threaded program which it maps onto a bunch of cores which are executing concurrently. So in some sense, it's competing with itself. So if you commit, you get to the end, you do all your updates, and you had no conflicts, then you release the lock, you discard the log, and you're done. If, on the other hand, you decide that you deadlocked or you ran into a lock conflict, then you can apply the undo log. You roll through and you execute all of the inverse operations while you're holding the original lock to make sure that there's no synchronization conflicts. And then you apply the undo log and release the lock, and now you've restored the state, and now you can run it. You can start over and try again. So, yeah. You need to have deadlock if you wait. If you don't wait, if every time you see a conflict you say, oh my God, roll back and start over again, then you don't need a deadlock. It would help to have a kind of a priority system to make things go through. One thing you could do is you can say, well, if I see a conflict, then I'm just going to run sequentially at the end. We're going to do something a little more sophisticated here, but dividing things into a concurrent phase where nobody conflicts with anyone and a sequential phase is a pretty good heuristic. But this being an academic paper, we're going to do something cooler than that. So the risk of the miners, conflict resolution means delay. So if everything conflicts with everything else, then you would have been better off doing things sequentially to begin with. So there's an assumption here that conflicts are actually rare enough to make all of this worthwhile. On the other hand, which means that if you're trying this fancy concurrency stuff and there isn't any concurrency to be had, then you're at a disadvantage to the simple-minded competitors who are just doing everything sequentially. So this is a kind of a caveat. If you think that concurrency, that there isn't much concurrency, then don't do this. And there's something else that you're not paid for aborted steps. So if you do something and you need to roll back, You can only charge the client for steps that you actually did that are committed on the blockchain. You know, if you run along a transaction and then it has to roll back, then you kind of speculated and you have to pay for that speculation. So these are reasons why you might think twice before trying to do things. Benefits are if there is low conflict, then there's a lower latency because you're doing things in parallel instead of sequentially. And assuming that the overhead of doing all this stuff isn't too high, then you win. Lower latency, if you're faster than your rivals, you're more likely to win proof of work consensus. Because in all of these things, you execute the contracts before you do the proof of work. And multi-cores use a lower energy per computational unit than single-core machines. And you're also making better use of your hardware. You know, it's really hard to buy a single-threaded server these days. So if you're going to buy a 64-core server anyway, then what are you going to do with the other 63 cores? Now, let's go back to Yudah's question. So validators, though, have kind of a problem here. The validators can't do the same thing. So what the miner did was the miner basically just lined up all these transactions, sort of ran them in parallel in a non-deterministic way, figured out a schedule that was equivalent to a sequential schedule, but the construction of the schedule was non-deterministic because it's based on race conditions, who gets the lock first, and so on. And if a miner tried to do the same thing, they might come up with a different schedule that is itself valid, but not the same as the one they're checking. So they're going to look at this and say, wait a second, the hash of the final state is different. This is no good. So we need some way to have the validators reconstruct what the miner did without doing the exact same thing. So our discovery of this concurrent serializable schedule was non-deterministic. We don't want the validators to do the same thing because they might find a different serializable schedule. And they'd have no way of telling what happened here. So instead, what we're going to do is the miner is going to post the schedule that it used, that it discovered. So it's going to first, throw all of the transactions into the pool, let them fight it out, and then come out with a concurrent schedule that the miners can check. And so the idea here is we want the validators to replay the miner's actual schedule. So we need to do this in a way that's deterministic because they have to get the same answer each time. It has to be checkable. So
the validator becomes sequential.
Say what?
How do you do parallelism in the validators?
That's a very excellent question plus 2. So of course nobody trusts anybody. So if the miner says this was my concurrent schedule, behold it's serializable and so on, you can't just replay it and check the final state. You better make sure it really is a serializable schedule, because otherwise, you could cheat, or the miner could cheat. And we're going to do this in a way that doesn't require locks and synchronization, because after all, it's got to be deterministic. So what we're going to do is we're going to steal yet another idea, but not from databases this time. We're going to steal the idea of fork join scheduling, which is kind of a school of parallelism. So what we're going to do is for each of the locks that we acquired, we're going to track the number of times the lock was acquired. And basically the schedule is going to say, well, at this point, we acquired a lock and it was the second time it was acquired. And so then each of the threads keeps track of sort of the version numbers on the locks that it saw. And this is going to be part of the schedule that the miner produces. So it says that when you replay my schedule, you're not actually going to use locks, but you're going to check and see if you had used locks, that the version numbers are the same as in my original schedule. This is a very cheap way of guaranteeing that the miner isn't cheating by pretending to, by basically breaking the lock discipline and not telling you. So what happens here is that if we're in parallel, these two things happen in parallel. The versions of the locks that they saw, for example, this one sees that the lock had a version number 0. It's never seen those other two locks. This one says the blue lock was 0. It's never seen the other two, and it's okay for them to run in parallel because they haven't, neither one has acquired a lock released by the other. Here, however, this saw lock version 0, this saw lock version 1. These have to run sequentially because it says that this one released the lock that this one later acquired. So if your lock version number is higher, that means that and this one is lower, that means that this one acquired the lock and this one later acquired the same lock. So they must run sequentially. So you don't have to actually acquire these locks, you just have to check that this is what happened. And so what you end up with is you come up with a fork join schedule which says that I did this transaction, these two were in parallel, these were in parallel. Each arrow is some kind of a dependency. And what you end up with is this DAG. And the nice thing about these kinds of DAGs is there are very efficient work stealing scheduling algorithms that say no matter how many processes and cores you have, we can be within a factor or two of the optimal schedule for executing these. So what the miner gets is this schedule saying, this is the schedule. You can do it sequentially if you want. If you have more cores, then make sure you execute things in this order. You can use the lock version numbering to check to make sure that there are no actual dependencies when you execute things, so that the schedule I gave you really is serializable. So basically, the miners discover in a non-deterministic way a parallel schedule. The validators replay that schedule. Yes?
Why the miner would write to sequence of nodes?
So what's the motivation for the miners?
Yeah, because if you just did if I did everything sequentially and just lose some time checking it,
No, that's also a very good question, which is like 2 slides away. No, so the question is, so the miners have an incentive to execute these things in parallel because they can respond faster, but why would they share this information with the validators? Why wouldn't you just tell everybody, oh, here's the sequential schedule, and slow them down, and you use your parallel, then you start building on your parallel schedule again. So this is similar Silk language, easy to schedule efficiently. We can check the validity using the version numbering thing. And there are no actual locks here. There's no locks and no rollbacks. There's only barriers and there's only forking and joining. So the question is, well, why would I share my highly parallel schedule with my rivals? So I figured out a way to execute this block quickly. And well, the answer is that, well, one thing you could say is, well, I could get a bigger reward if the critical path of the schedule that I provide is shorter. But there's a more elementary reason, which is actually, this makes, if you have a highly parallel schedule, that makes your block more attractive to build on, because I'm looking at 2 blocks. One has a sequential schedule. One has a fork join schedule. The fork join schedule I can validate faster. So why wouldn't I validate that one and then build on top of that one? So it makes it a more attractive candidate to build upon. Good. Everyone believes that. Okay, so the next thing that we did was, so we were working on this a few weeks before the paper deadline. So we had to put together some benchmarks, because conferences don't accept things unless they have benchmarks. And so the benchmark that we did isn't like the world's best benchmark, but it's certainly the world's fastest to put together benchmark. So we started out, with a 4-core server, not because it had a lot of cores, but because that's what I had sitting in my office, and I didn't have time to find another one. There is no concurrent EVM. I don't know if there is now, but certainly 2 years ago there wasn't anything like that. So we used a Java virtual machine, which has lots of concurrency built in. We ran Scala on top of it because Scala has lots of useful libraries. Because we needed all this transaction support with locks and undos and so on, we ran something called Scala STM, which comes out of Stanford. I mean, you're starting to get the picture here. We have a way of running boosting on top of this, which we call the Proust boosting library, which was our own work, which was generated for other reasons. So we piled that on top of it. So what we have is probably the world's slowest simulated blockchain, almost as slow as the actual thing, I suspect. But we were able to basically, so we took a bunch of contracts and translated them out of Solidity and into Scala, using our libraries to instrument the basic data structures. So when we ran the benchmarks, we ran the JVM with the JIT turned off. This, of course, slows everything down by an order of magnitude, but we're interested in comparative numbers. The problem with the JIT is it wakes up and it makes things super fast, and then it turns itself off, makes things super slow. And it's really, really hard to control when it turns on and when it turns off. And if you run the same experiment 100 times, you get 100 different results. So we turned off the JIT. We ran 3 cores, one reserved for garbage collection, because garbage collection also wakes up at the wrong time and stops everything. So we started running single benchmark blocks, and then we ran mixed benchmark blocks. And then we would tune the conflict rate. So again, these numbers are kind of exploratory. This would never get into SOSP, but it would get into PODC. I don't think, in principle, it would be hard to redo these in a much more rigorous way, but we never quite got around to it. Other people have, followed up on this and done kind of more extensive.
What kind of transaction use? What kind of transaction use?
We went to the Solidity documentation, where they had a bunch of sample transactions, and we translated them. There's one where voters register and vote. So for the benchmark, we have all the we would just have to have the voters register and vote. Tunable conflict is that we would have some voters double vote, because if everybody behaves themselves, there's no conflict. Yeah, so it's only if you try to vote twice that there's a read-write. So there's no conflicts if everybody just registers and votes. By cranking up the number of double voting attempts, then we can control the conflict rate. So this is a way of measuring how bad things get. And here, with effectively three cores, we get almost 2. This is the round is how much speed up the miners get. The green is how much speed up the validators get. Remember, the miners are using this locks and instrumented data structures. The validators are running this fork join, this silk-like fork join schedule. This is a 15% conflict. Here we Here we look at the rate of conflicts, and again, we do get some speed up. It's relatively flat along. It's not sense. You would think that the higher the conflict, the slower things are, but
it looks like it then even it picks up.
yeah, well, I think that sort of is probably not. You should think of these as being kind of flat.
Even then, it doesn't pick up.
Um,
Why is the conflict increases
Probably because everything else is so slow. We took another auction from Solidity. Bidders bid, request refunds when it's over. Tunable conflict is you could do bid plus. You can increase your bid by 1 versus refund. That's a data conflict. So here, what happens is here we crank up the number of transactions at a 15% conflict rate. I mean, we have, the paper has different rates. This is kind of, and here the speed ups are about the same between the miner and the validator as the number of transactions goes up. The speed up over sequential goes up slightly. As here, when we crank up the conflict, things go down. So at this point, you would have been better off running everything sequentially because there's so much conflict. You're spending all your time rolling back and redoing stuff. So this is more EtherDoc tracks document metadata. A tunable conflict is transferring documents versus queries. Here, there's a bigger gap between the miners and the validators. The miners get a little bit of speed up. The validators do better. Again, this is the number of transactions, 15% conflict. Here, what we see when we crank up the conflict is that the miners suffer, but the validators can execute the fork join schedule without much.
How are you measuring the conflict percentage?
Beg pardon?
How are you measuring the conflict percentage?
Oh, so we have operations where we know that they pairwise conflict. So these are the number of transactions that conflict. So here, for example, every pair of transactions conflict. At the other end, no pair of transactions conflict.
Can you please go back to the previous slide? How you have written in the x-axis is 15% conflict?
Beg pardon?
How you have written like it's 15% conflict?
Oh, 15%. That says that 15% of the transactions have a conflict.
So it's a dynamic one. So how can we know in the early hand that it's 15% conflict?
Oh, because we know exactly what this is only one contract, and so by adjusting the parameters to the contract, we can say these two conflict and these two don't. So because we know exactly what's going on, there's sort of no mystery about the conflict rate. So everybody's running the exact same thing here with different arguments to the calls. So so it's very controlled. Then we mix things equal proportions. Here this is the speed up as the number of conflicts go ahead at 15%. So it looks sort of like what you would expect. More transactions. You get throughput increases basically flat beyond that point. Here we crank up the conflict percentage. Miners suffer because they've got to do a lot of rolling back. The validators don't have to roll anything back. So, none of these things is particularly definitive because it's a very small number of cores running on multiple layers of software. But at least it's not if it were a total disaster, then that would raise questions. The fact that we get modest speed ups says that this is probably worth paying more attention to. So conclusions, speculation, this is hardly surprising. So speculative execution works if we keep all the threads busy and the conflict rate is low or moderate. It would be, you'd hardly expect anything else. And with only 3 threads, we do see some improvements. If that paper had been rejected, we probably would have had to go over and redo the experiments on a larger platform, which in retrospect might have been a good thing, but it got in, so we didn't bother. Future work, I think it'd be interesting to look at a multi-threaded DVM. I think such things probably exist at this point, but there are interesting things there. This isn't really compatible with Ethereum as it is because we're sending around fork join schedules to miners. There may be a way to kind of finagle this, but we never really pursued that. What happens when you have more threads? There's still, I think, some work being done on incentives. Our claim is that if you can produce a highly parallel schedule, you're more attractive to build on than if you can't. We have no empirical evidence to back that up, but it seems sort of plausible. There's opportunities for finer grained concurrency. So you remember the example that we had where we were incrementing Alice's counter. The naive, the kind of analysis we did was if I'm giving Alice 5 more and you're giving Alice 3 more, we would view that as a conflict because of read-write conflicts. But if we were smart enough to recognize that this is actually an atomic increment, then, well, atomic increments commute unless you overflow, which is a very rare event. So being able to reduce the conflict rate by taking advantage of semantic knowledge seems like a very promising area to go in. And in fact, we have some research.
There's also money attached to the different increments. This increment will gain $5, but this increment gain you $10. So maybe
No, but they commute. In the end, you end up with $15. And so it doesn't matter. If you recognize that it's an atomic increment, then it doesn't matter what order you do it in. But if it's a read followed by a write, then that looks like a conflict. And since most of what contracts do is incrementing and decrementing counters, it's just it's mappings plus arithmetic.
There's no way, since essentially the whole thing is sequential, there's no way to define, get paid for defining and some validation of a state that once validated, you don't need again and again forever like the...
Oh, that's not our doing, that's Ethereum's doing. If you were doing this in Hyperledger Fabric, then you would, the miners or validators, which are called, I think, slightly different things, basically you're running PBFT. The validators in PBFT would have to execute the contracts in the same way. They could also use parallelism to speed things up. But once you do the PBFT, you have finality, so the decision is done. You don't ever need to re-execute them. But that's a feature of permission PBFT-based blocks versus proof of work, no finality blockchain systems. That's not our doing. Here we're living with the no finality, execute things first, and then do the consensus. Whereas PBFT and others, they do the ordering first, and then the execution, and then at that point it's done.
In some way, but in the same way that we accept that, after 6 blocks, something is with high probability will stay there forever, you can also suffer a state that essentially will stay there. The state doesn't have, we may be here and agree on a state in the past, and from now on we don't need to go beyond this past.
If I'm setting up a new full node and I'm totally compulsive about it, then I've got to go back and replay every transaction ever.
You're compulsive. Yes. And what was the last question? Why the two? What movie is the two girls, and why this is forever?
Oh, this is from The Shining.
The Shining.
It's always dangerous, using cultural references with people who are out of touch. But no, I won't. Look it up on YouTube. It's one of the scariest moments in modern film. Okay, lunchtime. Yeah.